So it might be a little rusty. Apologies for that. Yeah, so as he said, I'm an associate research scientist at UC San Diego. And today I'd like to talk to you about some research I've been doing for quite a while, actually almost 2 decades now. I started when I was a graduate student back in 2005, not to date myself. So while my name and information is given up there, what's lacking is the names of people who have helped contribute to this work over the past 2 decades, of which there are many. Some of them will show up in the various citations I'll put on there, but I'm also very grateful to them for all of their help in me in doing all of this research. All right. So I'm going to give you a primer here, and I'm going to admit it's going to be a very, very abridged primer on planetary system formation. I'm going to stick to just a few things I care about in terms of what's relevant for this talk. So you're probably aware, stars form out of clouds of dust and gas. Protoplanetary disks are generally mostly gas and small dust grains when they start. And through various processes, those grains grow into bigger and bigger sizes. And eventually, these things begin to collide. So it's the collisional processes of the planet formation review here that I'm interested in. I want you to remember. Collisions happen, they build up in the bigger and bigger objects. Eventually, the gas that is there in the disk begins to dissipate. And so that's when we get into the kind of a demolition derby between the remaining bigger objects. So you get things up to the size of maybe Earth or a little bigger in the interplanetary system. Without the gas there to dampen their orbits, they can smash together. It's kind of winner takes all. Whoever's the biggest gets to keep all the mass, gets to keep the orbit. That's the planet at the end of the day. So after that, you might think, oh, okay, all of the chaos of planet formation is over. Things will be nice and quiet for a few billion years. Well, that's not the case. Let's just take our own solar system as an example. Here's the interplanetary system that we reside in. Green dots are main belt asteroids, and these red and yellow dots are near Earth objects. We, of course, are the third dot from the sun. Notice it's not all happiness. Lots of things are crossing very close to each other. Thankfully, collisions are not too common. This is a present day snapshot of the inner solar system. But things do happen. The collisions do occur, generally with smaller objects. Most of them seem to hit Russia for whatever reason. I don't need to talk about that. So the planet evolutionary process still involves collisions. Collisions are an integral part of the formation of rocky planets like the Earth, and they continue to be important for the evolution of these objects going forward. So if I want to go looking for evidence of these collisional processes happening around other stars, then I should look for what is released during the collisions, which is dust. So in this image right here, you have the Zeneca light. All right, I cheated a little. That's mostly comet dust, but whatever, just pretend. It's still dust in the interplanetary system. In this case, detected via scattering. We don't detect too many interplanetary system disks via scattering yet. Maybe with the next generation of flagships that NASA will build. So instead, we have to look for indirect indications that this dust is here. So not only does it scatter light, it also absorbs starlight. It's heated up to a temperature that's characteristic of its orbit around the star, and it re-radiates it as a black body-ish sort of thing. So get familiar with these kinds of plots right here. It's a spectral energy distribution. I am going to be showing them a lot. So what we got here is flux, typically broadband flux measurements as a function of wavelength. Sometimes there's some spectra in there. So if you're looking at shorter wavelengths, so like a micron and shorter, then you're typically detecting emission from the star itself. And so we fit here in this brownish line, a stellar photosphere emission model that fits all of those shorter wavelength data points. And we can use that to extrapolate to the longer wavelengths, where we are making infrared measurements to look for the presence of dust. So we say we have an infrared excess when an infrared measurement is well above that line there, indicating that there is some other thing orbiting with the star, small dust grains, absorbing that starlight and re-radiating it. So in this particular case, we got lucky. Not only is there dust orbiting around the star absorbing light, it's actually small enough that you get a solid state emission feature. So that's phonon resonances in the dust grains themselves. How exactly your feature is going to look is dependent upon what your grains are made of, what kind of crystalline polymorphs they are. All these various parameters impact the shape and structure of that feature. So this particular object right here, BD plus 2307, was published by Insik Song in 2005 in Nature. This object happens to have about 1 million times more dust in its interplanetary system than our sun's zodiacal cloud. So that's a lot of dust. What do we think created that? I'm going to continually come back to this kind of interpretation throughout the talk. But if you, in the case of BD plus 2307, it actually is 2 stars, not 1. They orbit on a 3-day orbital period, and they happen to be about 3 billion years old. We finally got an age for these stars. We were vexed because, you know, stars are really close orbit. They tidally lock, and then chromospheric emission is useless. You can't age date a star that way. So what we got actually is BD plus 2307 has a white dwarf companion. Yay, white dwarfs. We were able to age date the white dwarf. It's about 3 billion years old. Therefore, we can say that this is it's a mature planetary system. So when Lynette Cook made this nice artwork for us, we had that idea in mind. And we said, we don't want forming planets, we want old planets. This is actually, you know, pretty close to the age of Earth, right? 3 billion years, 4.5 billion years, whatever, you know, it's factor 50%. These really could have been full form mature planets colliding, producing all of this dust. All right. So what I'm going to go through right now is a bunch of case studies of particular objects that my team has discovered over the past 20 years, published and characterized. These are not the only dusty, really dusty stars out there. I'm only going to talk about mine, of course.
What's the separation between the white dwarf and the
8 arc seconds? It's about 90 parsecs, I believe, to BD plus 2307. So yeah, it's close to 1,000 AU in projection.
It's not provoking the collisions that were created to dust.
Well, I'll get into that later, but it could have some impact. We'll talk about that. Don't worry about it. All right. So let's fast forward a little bit. In 2012, I published a paper in Nature on a very unusual, very dusty star. Does anybody remember the disappearing disk star?
Yes.
All right, at least one person. That's good. I'll take it. I'm going to do a very brief review of it because I want to get into the present where we are trying to do follow-up studies on it. So I'm going to very quickly go through what we found in 2012. So actually, this is one of the first stars I found doing my thesis research, looking for stars in the IRAS database that had huge amounts of dust. At the time, you can see the IRAS data points, 1983, those little blue squares. It was insanely dusty. So I'm going to use the terminology of fractional infrared luminosity. And I hate saying that. So sometimes I might just say tau instead. It's kind of like an optical depth, but it actually isn't. But just go with me because I hate saying fractional infrared luminosity. Anyways, this disk that was around the star when IRAS observed it was absorbing about 11% of the starlight. That was, you know, like almost a factor of 10 more than anything we had seen at that point. So when we first saw this, we said, well, it's probably a protoplanetary disk, right? It can't be a debris disk, where debris disks are, of course, being smashed together in a mature planetary system making dust. So we did feed it into our Gemini follow-up program. And we got some T-Rex measurements of it. And it looked like it was a very dusty star. We're like, oh, cool. In 2009, it actually got observed again by T-Rex. It was almost accidental. We didn't actually request that. But it's a miracle because it was a factor of 4 lower than the initial measurement we made in 2008. At the time, again, we had no context, no precedent. We said, geez, maybe T-Rex did something wrong. Let's just ignore that for now. And it pains me to say that in front of a bunch of Gemini people. I love T-Rex, okay? I wish you'd bring it back. But that's what I thought back in 2009, okay? So we waited and, you know, we twiddled our thumbs and we waited for more data to be obtained. WISE measured it in 2010. WISE said, hey, there's no dust. Now things got really weird. And I said, this is nuts. Like, what's going on? I mean, we haven't seen anything like this before. So I petitioned the director at the time. I said, hey, I've got an approved program. Can you just observe this thing right now? I want to publish it. And they did. And lo and behold, T-Rex 2012, no dust. So, I mean, you take away all the other data that's on that plot. There's a lot of data on there. We kept measuring it because we just couldn't believe what we were seeing. Just T-Rex alone, right, tells the story. This went from being an insanely dusty star, reprocessing almost 10% of the star's light back into the infrared, to, in a period of a year or less, disappearing, gone, vanished. And that was the state of affairs back in 2012 when I published this. I have been following it up more. And that's what I want to talk about you more. So for those of you who are aware, T-Rex and Michelle, unfortunately, for those of you who know who Michelle was, aren't really available anymore. They were decommissioned not too long after I took that last measurement, unfortunately. So
Shell can still be available on IRTF.
I know.
No, you could.
Well, actually, they're using one of the chips for Mercy, aren't they?
What?
For Mercy on IRTF, aren't they filtered?
No, but or you could.
Okay. That's what I'm doing tomorrow.
It's been up installed once last year.
Yeah, but it's not on the 8 meter. I need a bigger telescope. So you notice the flux density here. It's 10 millijanskis. You need an 8 meter class telescope to do that. You just can't do that with the RTF. You could do like maybe 100, maybe 50 millijanskis with the RTF if you like want to just sit on it forever. Maybe I'll ask. I don't know. Anyways, so that happened, and I was in despair because I needed access to a mid-infrared imaging camera, a sensitive one, and a big telescope. Europeans, turns out, aren't very forthcoming in giving U.S. astronomers time. I kept trying. I wasn't getting anywhere. And this is what happens when you're desperate. I had a Subaru night with comics. Who remembers comics? The cooled mid-infrared camera and spectrograph. I like that instrument too. It's also decommissioned now. But I was on it in 2013 and I said, damn it, I'm gonna preserve this thing. I don't care. I've never seen people look at me so weird. Because yeah, I was pointing an 8 meter class telescope right above the ocean, 15 degrees elevation. But hey, you know, it's better than nothing. Anyways, I got that upper limit here. It's not good. It's 50 millijansky upper limit. I mean, of course I'm not going to detect it, but at least I could say, hey, it's not back, right? All right, I kept trying for VLT time. Eventually I got some. They said, okay, we'll let you get on here. Maybe it's because I added European people to my proposals, who knows? So in February 2016, I finally got VLT to point at it. And lo and behold, nothing was happening. We sat around, we published that one. Moritz Gunther published it in 2017, AppJ. Just last year, I went back to the VLT. I said, hey, let's take a look at this thing again. You know, for all we know, it could be back. Nope, not back. So I could probably observe it again. Grant Kennedy, who was one of my European collaborators on this, actually suggested, well, instead of calling it the disappearing disk star, maybe we just call it the disappeared disk star. So what's going on here? Like we had this huge, vibrant, dusty disk, and then that threw in a planet because that's probably what's happening. And in a period of a year or less, just gone. So what the heck happened here? I am not going to go into all of the interpretations that we came up with in the Nature paper. I'm going to invite you to go read that. Instead, what I'm going to do is try and tickle your brains with the puzzle, because we don't know really what happened here. One star did this, as far as we're aware. We haven't seen any doing like this, anything like this since. And we're trying to come up with any model that we think could possibly explain it. So the only thing that's really relevant here are the facts. So the facts are this: before 2009, it looked like there's we could fit the dust emission with the black body of having a temperature of about 450 Kelvin, assuming those are black body grains, which is not necessarily a good assumption. That would put them about half an AU away from the star. 11% of the starlight's been intercepted and re-radiated. You probably need dust, small grains, dust mass of something above 5 times 10 to the 21 grams. We can only put a limit on it because we only had a couple of measurements around the peak of the black body. If you want to measure dust mass as well, you need to go way down the Rayleigh jean's tail, which we could not do. All right, because the dust was so rude and it disappeared. Otherwise, if I knew this was going to disappear, I would have been like, give me everything you got right away. But I'm not that prescient. So post 2009, why is the text maybe a little bit of an excess? Maybe it could be like a weak asteroid belt or something. So what we can do is we can constrain the amount of dust for the remaining for the 450 Kelvin component. Any fractional infrared luminosity associated with that dust at this point in time cannot generate more than 0.05% tau. So what does that mean? We can scale that fractional infrared luminosity scales the grain size to -1/2 power. 2 different fractional infrared luminosities. We can say that grains with radius up to about 1 millimeter had to be removed from this system. So now we can actually start talking about physical models that could remove those kinds of dust grains. The interesting thing is, depending on some models you might choose, it makes a prediction for when the dust should return. So if I only remove grains up to 1 millimeter, then I can calculate how long before those millimeter grains repopulate the small dust population, and I should start to see the dust return, right? So if only grains up to a millimeter in size are removed, then it's a decade. Guess what? That's passed, and the dust isn't back yet. So I guess things bigger than that were removed is the way I'm interpreting that. I'm not certain. We need to, well, I'm an empiricist. I'm just going to keep making measurements of it. It's what I do best. I'm not a theorist. I make bad theories. Don't listen to my theories. Other people make interesting theories. Rachel Austin had an idea that a coronal mass ejection, a huge one, cleared out all the dust. Jury's still out on that. Anyway, so we have a very much a puzzle here. So one thing I've kind of ignored up until now is the star itself, right? Is there anything special about this star? And the answer to that is no. So this is a roughly 10 million year old star. It's in the Scosen complex. Here you just have it on a color magnitude diagram. It sits happily in the 10 megayear isochrone. Over here we have X-ray activity. Moritz Gunther was so nice as to point Chandra at it. It's pretty typical for a star of its age. Stars of its age are this kind of pink chalky looking line there. It has a rotation period of like 3 days, whatever. You know, it's boring. If you didn't know about the dust, this would be the proverbial flyover star. Oh, look, another 10 mega year old star in the Scosen complex. Who cares, right? Well, the only reason we care about it is because it's got all that dust. But otherwise, the star itself is very normal. And I want you to remember that. I'm going to come back to that in a bit. But for now, let's move on. I want to talk about those solid state features a little more and the kinds of dust that we see orbiting around these stars. So we've known about very dusty stars for, probably since the IRAS days. And so we have been able to obtain a decent amount of mid-infrared spectroscopy of them. A lot of stars were actually able to be observed with Spitzer in the IRS spectrograph. So really high quality spectra. And so we have seen a range of different emission features indicating pretty much all silicate dust. So on the top here, you have some exemplars here of olivine and pyroxene. This 10 micron feature here is from amorphous olivine and pyroxenes, whereas the crystalline shoulder here, about 11.3 microns, is from cooler stuff like, crystalline olivine and pyroxene, which look far prettier than, random sand grains, whatever. On the bottom here, you get some interesting ones. They have features that peak at about 9 microns. That's actually indicative of SiO2 and particular polymorphs, you might get obsidian or tektite or something like that. But again, it's all very much silicon dominated, indicative of the kind of stuff we see in our own planetary system. The particular feature strengths and stuff is telling more about the physics of the collision. Silica like this is more indicative of very high energy impacts, which generates SiO2, and specifically polymorphs like tektite, which require very high energy and then rapid cooling. Whereas the olivines and pyroxenes could be just glancing blows, just scrape some stuff off the surface or something like that. So what about this thing in the middle? I don't have a picture for it because I have no idea what it is. And you might be looking at it saying, it just looks like a black body, right? What are you getting all worked up for? Okay, so I'll zoom out a little. So in 2013, I published 2 stars. You can tell from these spectral energy distributions, these stars are A-type stars, early type stars. Temperatures about 9,000 Kelvin. And all of them have infrared excess emission, not only in the interplanetary system, but also indicative of outer planetary system material. So Lynette Cook put together this nice diagram here, comparing them against the solar system. You have this inner hot dust region, the terrestrial planet zone, and you have this outer cold Kuiper belt-like dust region. But what about those mid-infrared spectra? So if you look right here, you can tell this green line here is the spec spectrum we got of this star. And it's kind of starting to turn up at about 5 microns. And then it got to go up, and somewhere around 8 microns turn over and come back down. That's not a feature we've ever seen in any other main sequence star before. So we published it and said, hey, look, something else we don't know what it is. And then in 2017, Casey Lease found another one, HD 36546. So these stars are all young. I think HD 36546 could be about 5 million years old. It's in the Orion constellation. It's not necessarily part of any of the Orion star forming complexes, I don't think. These other 2 stars that I published in 2013, those are from Upper Centaurus Lupus or Lower Centaurus Crux era regions. I think all that stuff's been reshuffled now, right? With Gaia, I don't even know if I say that, if it even means anything, but they're young. They're like 20 million years old. Okay, so let's talk a little more about their planetary systems themselves. So stars, all of these disks have been resolved. What a difference 10 years makes. So a variety of wavelengths too. HD 131.488 is a beautiful edge-on disk in this image. It's been resolved with ALMA. We also have some scattered light observations with GPI and sphere. HD 121.191 happens to be face-on. I don't know how they worked that out. They must be talking to each other. But anyways, it's got a pretty significant extent. And this Herschel data that we took, Laura Viken published in 2016. It looks like it's about 3 arcseconds diameter. HD 36546 was imaged by Thane Curry with Subaru, and it's about 1 arcsecond-ish. So all the disks are, the outer disks have been resolved. We haven't resolved the inner disks, of course. Those are very small angular extent. What's interesting, these have all been followed up with CO spectrometers in the submillimeter, and they all also have CO gas, molecular gas, detected in their outer planetary disks. So this might make one think, okay, well, where is this CO gas coming from? It's not primordial. So it's not like these are just some, very young stars with protoplanetary disks. These are, there's no evidence of accretion or anything like that. They're not like transition disks. The prevailing wisdom now for CO detections in, sort of A-type stars, or even I think there's a couple, maybe a few G-type stars now with CO detections in their outer disks, is that there's actually a significant dynamically hot, icy planetesimal population, comets. I'll just say that. They're like comets. They're smashing together. They're CO rich. They release a lot of CO gas and stuff like that. So that's why these things are probably detected out in the CO. So how is this for an interpretation? You have lots of dynamically hot comets. They're whipping around. They're smashing together in the outer planetary system, making gas and dust. Why can't a bunch of them just be going into the inner planetary system and being, sublimated or whatever, destroyed? Okay, so let's try that for a model. Casey Lease came up with this particular model here. You got some water gas. Comets are mostly water. So you vaporize a bunch of water with a big high energy impact in the interplanetary system. It makes these 6-micron features. You've got some SiO gas we threw in there and some dust. You can have some amorphous carbon. There's probably, solid carbon locked up in there too. And then maybe some PAHs or something like that. Anyways, it's an interesting model. Here's the problem. I don't have this part of the spectrum. Oh man, how hard I've tried. I tried to get Sophia to observe it. We did eventually get some Sophia like 5-micron imaging. That's not very helpful. It's a broad filter, right? So I can't say if there's like these narrow gas features in there. So if I want to do this right, it's going to take something like the Webb. I keep asking. I think that's everybody's story, right? We keep asking. It turns out, actually, I think JBST has actually observed 2 of these stars at 4 microns spectroscopically. I'm not sure what those data show. I'm interested to see what they found. What I'm really interested to know is, why does that image of the Webb look like a star destroyer? Is that just me? Is NASA trying to tell us something? Anyways, keep your eyes out for their next project, I guess. All right. So maybe it's just a bunch of comets, right? Here's something even crazier I came up with recently. So I'm actually here in Hawaii to observe Arc-Corboreal stars. Does anybody know what Arc-Corboreal stars are? Of course, Tom does. So I'll give you a quick primer into them. Our corona borealis stars are supergiants, very luminous, and they are carbon rich. Their atmospheres show all kinds of carbon features, swan bands, all the fun stuff. The defining feature of an corona borealis star is that it experiences sudden and dramatic dips in optical brightness, sometimes up to 8 magnitudes. And it just comes out of nowhere. You'll just be sitting around and all of a sudden, gone. And then it'll like stumble around and work its way back. So these things are weird. They're weird supergiant stars with lots of carbon-rich dust orbiting around them. All right, we believe that the dust that is causing the dimming events is coming from the atmosphere and is itself carbon-rich. So in the Spitzer era, a few people investigated this. Garcia Hernandez et al. Specifically published a few papers on this topic, trying to characterize the spectral features of these stars and what their composition could be. And what their findings was that the best fitting interpretation on available lab data and stuff that they had that they could use was that these features are kind of like a PAH, a polycyclic aromatic hydrocarbon, except you take all the H out. So you basically just have a carbon-rich ring of material that is hydrogen depleted, which would be exactly what you get if you took stuff out of the atmosphere of an R-Corp star and let it condense into dust. So that's what Garcia Hernandez et al. Thought was the best interpretation for these spectral features. So here is an exemplar R-Corp star, Y Moose. I plotted its Spitzer spectra. I removed the continuum component of it just so we can highlight the dust feature alone and nothing else. And then I slapped the best spectrum we have for these weird dust stars with it there. And I'm not going to say it's not a good match, but I don't know, because I'm missing like 3 microns worth of data that would really give me the confirmation that this is what this thing is looking like. I don't know why a main sequence star would have that kind of dust. That makes no sense to me, because you're talking about a protoplanetary disk, which is hydrogen rich. Why would you end up with solid carbon grains with no hydrogen in them, or extreme hydrogen depletions? So I found something that matched. I'm just gonna leave it at that. I don't have an interpretation here because I don't understand how you would get that kind of dust stoichiometry. There are papers coming out. I think there's one actually like the other day on how you can get unusual C/O ratios in the gas, the molecular gas in protoplanetary disks by locking up the oxygen stuff, and ices and silicon grains and things like that. But that's just the gas. How do you then go into a solid that doesn't have hydrogen in it? I don't know, but it matches, and maybe I'll get a spectrum someday and I can see if this is still a reasonable interpretation, or who knows, maybe it's just a bunch of comments.
Our coronal borealis stars do have oxygen.
They have oxygen, but they don't have hydrogen. They're extremely hydrogen depleted.
Right. Yeah.
Yeah. So it's the formation of those carbon rings in a very hydrogen depleted environment that makes this specific feature. It's not, that's why it's not a regular PAH, right? A regular PAH would have a big, 11.3 and maybe a 12.7 feature. Yeah. That's how you get this, just the hump and nothing else. Right. There is oxygen. Okay, moving on in stars and age, we're going to bump ourselves up to 80 million years of age now here. We're looking at a star that's in the Alpha Persei open cluster. In 2012, we found this thing doing a survey of what with WISE. WISE was new back then, so why not look at every open cluster with WISE and see if there's any cool things hiding around. This is the only thing we found. But wow, it's a real record holder. It still is the dustiest main sequence star known. At an age of 80 million years, it has a hot inner dust component that re-radiates 16% of the star's light. It's truly gargantuan. So, we've been doing some follow-up studies on it, and most recently, Swetha Sankar in 2021 published a paper from our team on this object. She was an undergrad at the time, actually. She's now a grad student at Johns Hopkins and does radio galaxies, I believe. So if you're into that kind of stuff, look her up. But so we've been trying to figure out what's going on with this particular object. It's like a K2, K3 kind of star. And again, it has what looks like an outer belt of dust as well as an inner one. And there's a really bad comic spectrum there. It's the best I could do. I spent like 4 hours on this thing with comics. That's not very bright, right? This is like, 30 or 40 millijanskis. But I tried. I wanted to get something, and I sat on it forever. Now there are James Webb spectra that George Ricci and Kate Sue have, and I have no idea what's in them. But I published this anyways, and I hope they don't find that I'm wrong. But anyways, in case I'm right, let's just talk about this star. So George Ricci in 2021 published a paper about the same time. This paper came out where they monitored the star with Spitzer, warm Spitzer, looking for evidence of infrared variability. And it shows some interesting, ups and downs. And then right near the end of the Spitzer mission, the warm Spitzer mission, a big bump in the infrared flux. So you could probably take that as an indication of a fresh production of dust, small dust grains through a collision or something like that. So what's going on? Why is this star so much more dusty than all the other dusty stars we have out there? And what's with the variability? Can we find a model that kind of merges the two? So George thought about this extensively, and what he came up with is he says, all right, what I've got is an outer asteroid belt thing and an inner asteroid belt thing. And there's going to be a massive companion that is stirring up the inner belt. So this is going to have to be something in the mass range of like 1 to 10 Jupiter masses or something like that, orbiting the inner planetary system, making all these asteroids just smash themselves to heck. So in Swetla's paper, we took a look at companion mass sensitivity limits that we could put together with available data. I took a Keck AO image. It was not very deep, but it was sufficient to say that there's no stellar companions and wide orbits around or anything like that. We took a bunch of measurements with the APF, the Automatic Planet Finding Telescope at Lick Observatory. I also grabbed a 3-meter spectrum way later, just because why not? And there's nothing happening. If you look at these plots and wondering what you should see, there's nothing to see. There's no companion as far as we can tell in any of these data. So we put it all together. We said, all right, here's our mass sensitivity limits from the available data. And so all of these dots are solutions that are allowed. So remember, if you look back at that spectroscopic data set that I have on the left, you see all these little zigzags and things everywhere. Those are models that we're trying to fit that are in agreement with the data given the errors, right? So what we can do is we can take a look at that and say, what's the most massive companions we can allow here? And that's this line. Anything above the line, we should have detected. So let's go back to George's preferred interpretation. Taking everything that George put in his data or his paper, he says the hot dust is here, about 0.3 AU. Cold dust is out here, about 30 AU. And so he's going to need to have a companion somewhere between 1 to 10-ish Jupiter masses hanging out near what would probably be an asteroid belt in his model. And so it's got to be stirring it up. Unfortunately, our mass limits are not actually good enough to rule out all of his parameter space yet. So what I've been doing is I've been begging whatever high precision spectrographs I can to observe this star for me. If you look back here, these are not high precision radial velocities. I know I used the Automatic Planet Finding Telescope at Lick Observatory. This star is too faint. I can't use the iodine cell. I wouldn't have any flux left. So these are just your standard errors, like 100 meters per second or something like that. What I need is errors more like 5 meters per second. And there's only a few telescopes that can pull that off. Maroon X could pull it off, for example. And then I've been asking NUID. I don't know. We'll see if that if that goes anywhere. If I get really desperate, who knows? Maybe I'll put in a Keck proposal. What I really want to do is I want to push this line way down here, and I can do it. I just need some good precision RVs. So
Are there any sub-millimeter observations of this star?
none that I'm aware of.
Because that sounds like if it's so dusty, you should. So what's is it visible from ALMA, or do I need to?
Yeah. so yeah, it's in Perseus. So we have pointed ALMA at Perseus. So with John Tobin, we did a bunch of protoplanetary disk studies.
Well, the limit is about plus 35.
No, I can get to plus 50.
What?
ALMA can do plus 50. It's not good, right? So if you want to do something that's faint like
Well,
this, right? I wouldn't recommend it. Like, look, here you go. Here's 10 millijanskys, right? If you want to go out into 800 microns, it's going to be faint. No, I don't think ALMA's.
Noema would be another choice.
Maybe. I don't know enough about their sensitivity yet. So I'm happy to talk with you about that. Yeah, if you think this can be done, let me know. I do think that's a good idea. Yeah, we should definitely try and look at any way you can try and characterize it, right? Okay, so I'm leaving something out so far, and that's the mid-infrared spectrum. And so this is where our, in Swetla's paper, where we came up with our preferred interpretation, differs from George's. So here I'm plotting again some of those exemplar mid-infrared spectra from IRS. This is your olivine, pyroxene stuff. Here's a silica, and here's a weak dust star, HD 69830. It has a lot less dust around it, still pretty decent amount of dust, but a lot less. And so its mid-infrared feature is actually weaker. So if I'm trying to look at this data and fit something to it, then maybe I could squeak in an HD 69830, but I'm definitely not getting anything like, this huge dust guy, HD 113766. And that thing only has 1% fractional infrared luminosity, whereas B48 pair is 16%. There are no main sequence stars with dust indicating a fractional infrared luminosity of 1% or more with no mid-infrared spectral features except V48 pair. Now there's like 5 of them that we still haven't observed yet. Whatever. For the purposes of this paper, I was able to say this is weird. So what's going on? If we were to pretend that this thing actually has small dust grains, V48 pair has small dust grains, which seems reasonable, right? With as many collisions there is happy to produce a fractional infant velocity of 16%, there's got to be small dust grains. How much small dust grain mass do we have? It's probably in the neighborhood of, like this star here, HD 113766, like 10 to the 24 grams. If I try to fit this model for HD 69830 in there, that's like 10 to the 19 grams. So there's like lots of dust that I'm not seeing solid state emission features from. And why is that? So I can come up with two possibilities. One, it's all big dust grains, like 5 microns or 10 microns. That seems unlikely. So I don't like that. Here's another idea. It's a type of dust that doesn't make mid-infrared features. There's two kinds of dust types that'll do that: amorphous carbon and iron, metallic iron. So, all right, here's my preferred interpretation. I believe what we got here is a proto-mercury happening. So you're smashing something deep into its interior layers, you're releasing lots of iron-rich material, doesn't produce a mid-infrared spectral feature, but it's producing a heck of a lot of dust. So you just needed a really deep excavation, or a planet that's been pummeled so much that all that's left is its core. So anyways, that's what we put forward in Swetha's paper. What I like about the two different interpretations is that they're testable. You go back here, very easy to test George's interpretation. All we got to do is just watch this thing for a couple of years with a high precision spectrometer. Swetha's, we still can do the same. We shouldn't see anything like this. No big things floating around in the interplanetary system. It should just be small stuff. Maybe a super Earth somewhere, and that's about it. So two very different interpretations, very testable. Please give me telescope time. Okay, I want to move on to the last star here. Yeah, I'm going a little long here, so I'm going to try and speed this up. This is the most recent publication for me on very dusty stars. TICO 8304101. Phone numbers for stars are terrible. This star is, if you're looking at it, it's your typical run-of-the-mill super dusty star. It's it's like a G9-ish thing. It's got lots of dust. It's got a solid state emission feature. It's cool. Yeah, it's very dusty. Okay, cool. What was weird about this one is while I was gathering the infrared data, I was looking around at TESS, and I said, oh, I wonder what TESS finds for these stars. The rest of them are boring. This one, the observation TESS right at the very beginning, that's like a magnitude and a half dip. Like 70 to 80% of the light of the star is blocked out. Okay, that's weird. So what is this? Is this like some sort of stellar companion or something? We took a bunch of radial velocity measurements with Pharos in the southern hemisphere, stars at like -50 dec. Nothing. So it's not a star. Why? What's going on there? Well, we decided after looking at all of our various data sets that this is probably a giant star-sized cloud of dust, because we didn't see any radial velocity signatures. There's nothing, indicating a stellar companion that would have the size comparable to a star. So we started monitoring it regularly with the Las Cumbres Observatory Global Telescope. And I just in December wrapped up 3 years of monitoring of this star when it was up. It's up yearly from April to December. That's actually just becoming available right now. And so what I was looking for is repeats of these dips. I mean, there's just tons of variability. The star is just constantly having clumps of crap pass in front of it. But I was looking for something a little more repeatable. Is there, a periodicity associated with this? What's going on? And so I started collecting multi-band data. This is green is V band, red is R band, the black is I band. And I was just looking for repeatable dips. The I band actually turned out to be great for assessing these really deep dips. If the I band gets down to about 12th magnitude, that's a real deep dip. So I managed to collect actually a fair number of those things over the past 3 years. I just did this analysis last week, so this is fresh. I don't have like good interpretations and analysis for you. I tried to slap a period on here. So these up and down dashed lines are a period of about 167 days. And it looks like it does all right. We've got some problems though. First, no dip there. All right, well, I went and looked at that a little more carefully. It turns out, unfortunately, that was pretty early. I was like in April, the star is not very well up and the weather's not great. So there's a 3-day gap in the data. These dips are only 1 to 2 days wide. So it might've missed it.
I'm confused.
Yeah.
It's right next to it, a few 50 days earlier, there is a big dip.
Yeah, I'll get to
That
that.
doesn't match the,
I'll get to that one too.
where do you get the period from
I was just going off the I-band dips. I was just trying to line those up.
Okay.
But there's a problem. What about this thing over here? That doesn't fit. And then, yeah, you're right. These other dips over here, it doesn't match them either. And actually, I'm hiding a lot of lies in here. When I plot a huge data range like this, I can hide a lot of things. These don't actually match the minimum of those dips very well at all. So I don't know, maybe there's like a transit timing variation thing going on here. This doesn't look like a planet with a fixed cloud orbiting. I don't know what's going on. I don't know if it's like a cloud that trails a planet and processes. Like I said, I haven't done the analysis on this yet. Something is weird here. If I'm going to make a prediction based off of these dashed lines, August. So I'll try and get some data on August, I guess. But in the meantime, I don't know why this thing has the dips lined up the way it does. Actually, if I backtrack this back to the TESS epoch, the prediction is like way over here. It gets real off. So I wish I knew what was going on, but I don't. But in the meantime, let's talk about the star. I didn't tell you the age, and that was on purpose because it's old. It's an intermediate age. In the paper published in 2021, we came up with an age about 600 mega years. That was based on a non-detection of lithium in the primary star, which I am sad to say was a result of a Pharos detector artifact. There is a lithium line. It's not very big. So the age is probably closer to like 300 to 400 mega years. It's still way older than you'd expect for any star that's undergoing planet formation. This is not planet formation. Planet formation's been done. This is something else. But anyway, so we try and measure the age as best we can from other indicators, activity. The primary star with the dust, there's no real indication of activity. We're trying to measure a period. It's hard. And it actually has an M4.5 companion about 50 arc seconds away. So we measured the activity of that. And based on that, it's, we're like probably somewhere in the neighborhood of 300 to 600 million years old. We tried to slap them both on an isochrone. Guess what? One of the stars is super red because it's got all this dust around it. So doing isochrone analysis is rough. But as best we can tell from the companion, a Hyades-like age is reasonable. You can't really see the X here. It's right here. There's the companion. There's the companion. It's a little easier to see. So it sits actually happily in the Hyades locus in a Gaia color magnitude diagram. So our best estimate for an age was like Hyades-ish age. It's probably somewhere in the neighborhood of 400 mega years old would be my best guess at this point. All right, so let's do real quick population synthesis. I've only talked about a few of them, but there's a lot of these. There's like 20 of these really dusty stars known right now. So here I have plotted fractional infrared luminosity as a function of stellar age. I've got our blue dots. Those are A-type stars. Gold dots are F-type, or yellow dots are F-type stars. Gold dots are G-type stars. And these little red dots are actually K-type stars. I don't plot M-type stars. I don't like low mass things, sorry. Maybe somebody else can add them to this plot. They turn out actually to be really difficult and complex. Their protoplanetary disks last a lot longer for some reason. So some takeaways from this plot. I've got these two lines here. These lines are indicative of where I consider any dust above them to be due to a transient dust production event. So if you're kind of in the neighborhood of these lines or below them, then I say you're probably an asteroid belt and you're just kind of active for some reason. So a lot of stars can be described in that way. But then there's all these things, and they are way dusty and sometimes even really old. So what's going on here? If you want to come up with a theory that explains all of these different data points we have in this plot, it has to get a couple of things right. It has to get the age distribution right, which is only really come into focus in the past few years. And it was only in 2021 that I published a 600 mega year old star, and Attila Moore published a few stars that are about 200 mega years old. BD plus 2307 we've known about for a while. They only got a firm age estimate from its white dwarf companion recently. So you gotta get the ages right. You have to get the incidence rate right too. So as a function of time, only a certain fraction of stars will show this elevated amount of dust. So let's start with the young ones. What kind of explanation can I come up with for them? So for the longest time, our group was dead set on this being an example of the giant impact phase of planet formation, rocky planet formation, like, the Earth-Moon collision, right? you have the Earth, proto-Earth colliding with Theia, and you get the moon out of it. So those kinds of impacts should occur anywhere between about 10 to 100 megayears of age. So for the longest time, that was our preferred interpretation. Lots of dust, young ages. Yeah, this is planet formation. This is rocky planet formation. It's okay. So how about the incidence rate? So a couple of papers, we did that. It's about 0.5%. Well, then this thing Kepler came around and told us what the exoplanet occurrence rate looked like as a function of size and orbital period. And what they found is that for every FGK star, there should be about one Earth-like planet. These two numbers do not match up well. If every single star has an Earth-like planet orbiting around it, then why do only like 0.5% of stars in the relevant age range show the dust from their final formation processes? We don't know. This is a problem. Where are they at? So what we got to do here is dig back into the theory, which is not my thing, but other people do it. So Joe Najita, Scott Kenyon, other people have been investigating this. And let's circle back to the beginning of the talk. Remember when I said the disappearing disk star is normal? It is a typical star. What if every single star that produces lots of dust during the terrestrial planet formation process has it disappear on a short time scale? Well, that would provide an explanation for why we don't see enough of these things to be indicative of how many planets we actually see in that size range. That's ongoing work. They just published a paper about this year. I think it was like called Takeout and Delivery or something. They have cute names. But it's basically describing why does the dust we see from the expected planet formation processes not match the number of planets we see. So trying to match up these two things gives us actually a lot of insight into the planet formation process. And we just don't have the story nailed down yet. Speaking of which, what about all these old things? These are the ones that are problematic because if you want to have terrestrial planet formation happening between 10 and 100 megayears, fine, whatever. But after that, especially way after the, like, you know, a gigayear or more, why are there stars with so much dust around them? So I prefer an interpretation where we have some kind of instability happening. So in our own solar system, we had the late heavy bombardment instability, which caused an influx of impactors to the interplanetary system due to Jupiter and Saturn doing their weird stuff out in the outer planetary system. Similar sorts of things could be happening in other planetary systems. Even more violent things could be happening that could be actually causing full-fledged planets to smash together. So in a paper that finally got accepted in 2021, Isidoro et al. Actually did an investigation of a full-scale planet formation simulation involving all the greatest, latest physics, pebble accretion, all the fun stuff. And what they found is you can form pretty easily resonant chains, tight packed interplanetary systems. Who's familiar with TRAPPIST-1? I hope everybody's heard of TRAPPIST-1. Anyways, it's like 7 planets within an AU or something, right? Okay, so you can actually make those pretty easily, but making them be stable for a long period of time is not easy. And in fact, something on the order of 95% of those systems become unstable. Now, when they become unstable is kind of what Isidoro's paper was all about. And what he found is that most of them tend to become unstable pretty quick. So within 100 megayears or so, those systems are just destroying themselves. But he found an extended tail of events that goes way out to gigayear ages. Well, I like that because here we go. I've got an extended tail of weird things with gigayear ages producing lots of dust. So this sounds great. This sounds like, okay, you had what was a tight packed interplanetary system. It wasn't going to last. It fell apart. Things started to collide at some point. So he makes some very specific predictions about the architectures of these planetary systems, which I love, but I can't get time on telescopes for because, you know, they want to look at real planets, not possible planets or planets that are being destroyed. Anyways, I'll keep trying. But so a stable planetary system should look something like TRAPPIST-1, nice, happy, tight, packed, resonances, all that fun stuff. The unstable systems will be a bit more messy, but there's never going to be anything big in there. There's not going to be any like Jupiter-sized planets or anything like that. So you're going to have like some super Earths, maybe some sub-Neptunes, stuff like that. But there should be several of them, and they should be, you know, within, you know, an AU or 2 or something like that. Then recently, Brad Hansen at UCLA decided, well, I've got another idea. How about I put a moon around that planet? Now I've got a super Earth, and it's got a moon, and it's close enough to its host star that tidal interactions are actually destabilizing the moon. And you can actually get that moon ejected. And so here he's got simulations showing all kinds of planets that are being ejected. And this, in some cases, they come back, these red dots, and they collide with the planet that they was ejected from. In fact, that's the most likely outcome. If you can eject a moon orbiting around like a super-sized planet, it should come back and collide. And that should produce a lot of dust. So these are some interesting ideas. It's sort of different testable theories. I mean, Brad's paper, he only needs one planet with a moon, but there could be other planets there. So it's not necessarily completely decisive if you go and you look and you see multiple planets, like Isidore's system should look like. But anyways, it's something that's definitely testable. So I'll wrap up there. I've given a lot of information here. I hope I've convinced you of at least one thing. There are stars out there with huge amounts of dust around them, and that we don't necessarily have a great understanding of why that dust is there. My preferred interpretation is that there are some very violent processes happening between big objects. This isn't some collection of like an active asteroid belt or something. This is like really catastrophic collisions between planet-sized objects producing this dust. But we haven't yet gotten to the point that we can conclusively rule out any specific interpretation. We're really just kind of, it's amazing, 20 years after discovering these objects with IRS. Oh wait, IRS was 40 years ago. Ouch. All right, 20 years of me working on this subject. We still have only just begun to get to the point that we can like see the full picture, and we gotta like actually figure out what's going on now. So I'll end that there. Thanks.
Great talk, and you can monitor. Yeah, questions. Go ahead.
So I've got a couple. I'll ask the straightforward one first. So for the system where you're hypothesizing that there might be a proto-Mercury,
yeah.
What sort of spectroscopic traces might you look for iron species?
Well, yeah. So unfortunately, metallic iron doesn't have any like very specific features to it. So I think actually the best evidence is going to be what the planetary system architecture looks like for confirming that. So in this particular case, in order to get that kind of setup where you can have a planet being pummeled enough to get into its deep layers, I think you're going to need kind of one of these unstable, tight-packed configurations. So I'm hoping that if you get enough radial velocity monitoring of this, certainly you're not going to find a Jupiter or hot Jupiter or warm Jupiter or anything Jupiter-ish. And maybe you might find a few like super Earth size things would be, I think, kind of it would be supporting it. It would not be a smoking gun. I don't know what I would look for specifically that would say, yes, that is iron. It couldn't be anything else.
Right.
Yeah.
I tend to concur with the size distribution that would be the alternative hypothesis is quite difficult to explain.
The collision that produced the moon did not get down to the iron.
No, well, that was kind of a glancing collision,
yes.
As best I understand from the whichever models you want to use these days. Yeah, the impact parameter was definitely not a head-on. Yeah.
My second question was about you disappeared.
Yeah.
Right. So yeah, was you describing it, my first thought was some sort of central explosion like a CME as well.
Okay.
One thought that occurred to me is that, and maybe you can comment on observational constraints on this, but it occurred to me that if you have some sort of central ejection event that to basically blow stuff out of the way, the effect could probably be manifested with a weaker CME if the disk orientation was favorable. So in other words, if you're looking
relative to the rotational axis of
Yeah.
the star. Yeah.
Exactly.
Okay. Yeah. I hear you.
So my question, yeah, so you could, if a bigger explosion would let you move stuff out of the way, but it would have to be closer to or not. And so my question was,
for the sun, is there a preferred inclination of CMEs? Are they always in the ecliptic plane?
no, but I was thinking the orientation of the dust. If
Yeah.
the dust is in, yeah. So yeah, I don't know, maybe. I don't know much about CMEs, but
Yeah.
disk inclination was something I thought might be a factor, and that might allow you to lower the strength of the CME required a bit.
I mean, I'd love to figure out what the disk inclination was or is or
Okay,
anything at all.
so that's not known. That's kind of what I guessed, right?
Yeah, like I said, before 2009, there was no reason for us to have any sense of urgency.
Right. Yeah, it's a shame that it wasn't imaged before then. It would have been really, really helpful.
Yeah, and even now, I mean, there's a bunch of disks that, there's a couple that are known that Attila Moore found that actually are comparably dusty as this one,
Okay.
and none of them have spectra. And so, they're fainter. You can't do them from the ground easily. There's no infrared spectrographs anymore, anyways. In the northern hemisphere, a few of them are northern hemisphere stars only. So we're asking for Webb, but you know how that goes.
Yeah.
We'll see how that goes.
So one question about removing large dust grains. I thought it would be much easier to remove all the small dust by just radiation pressure, more or less.
So this particular star is like K2, K2.5. Radiative blowout is not as effective as Poynting-Robertson and gas drag. The gas drag actually is the primary culprit for grain transportation. Yeah, radiation blowout is not very effective. And so that actually feeds, one of the models we came up with was what we called I'm forgetting the name, it's like a dusty avalanche or something, or accretion avalanche. You remember it was invoked in white dwarf stuff. Well,
Right.
The word avalanche appears in there. I know that much at least.
Okay.
Anyways, what you do is you build up tons and tons of dust, and this works well if radiative blowout doesn't work. If radiative blowout is not sufficient to remove the grain from the star's gravitational field, then they'll just build up somewhere. They shouldn't spiral into the star, but maybe they don't for some reason. Maybe there's a gas component that kind of traps them. Eventually, you get so much stuff, you get an instability, and all of a sudden you accrete everything in a really short amount of time.
A long way accretion?
Yeah. Is that what I'm thinking of? No, maybe it's a combination of the two. Maybe it's runaway accretion. Anyways.
Yeah, we do have a question from the Zoom.
Okay.
From Ryan says, could these dust excesses also come from a planetary engulfment event?
Planetary engulfment, and not by the star, or is that what he's suggesting, by the star?
Yeah, by the star.
Okay. So you're imagining a scenario where you have a planet orbiting the star. Maybe it's inspirated and it actually merges with the star.
Yep.
Okay. So to get the dust like that, I mean, I guess I could imagine a situation where you might get the infrared excess, but it might be possible. I'd have to look at it a little more carefully. I haven't thought about that one in detail. Sorry.
Yeah, no problem. Yeah, just a thought.
Why do they have a lot of dust?
Well, so I mean, this happens actually in stellar mergers. Red novae, for example, are quintessential stellar merger events, huge outbursts of light, and then you get a big dust component around them.
The 838 bond.
That's a good one. But why not V13 and us go? Come on. That's my favorite. All right, anyways. So yeah, dust would be a byproduct. So, but the problem is you need a pretty massive planet to get enough mass out there. So you're not talking about rocky stuff anymore. You're talking about like a gas giant merging with its host star to get this kind of excess after the event. And then why would it be predominantly dusty? So I'm beginning to disfavor this because there would be a significant gas component. So actually, yeah, Tomek Kaminsky, I've been working on him with Red Novae, and he likes to do millimeter studies of these things, and he finds all of them cool molecular gas around them, and some really awesome like bipolar nebula and stuff. These things are gas poor as far as I can tell. Now, our sensitivity to gas is pathetic. I'll say that too, but there hasn't been any indication of gas around them. Actually, an interesting thing about the disappearing disk star. So this 2009 measurement with T-Rex, I happened to get a spectrum, an optical spectrum of the star with the Siding Spring Observatory, I think within a week of it. So whatever was happening to make this dust go away had no impact whatsoever on the optical spectrum. There was no H alpha line, there was no increased veiling indicative of accretion. The veiling was a weak limit, but there's definitely no H alpha. How's that? So if accretion or some sort of process that would produce a gas-rich disk had occurred, then I think we would have seen it. Now, there's one star I didn't talk about, and its name is RZ-PSC. RZ-PSC is accreting a planetary mass companion and has gas emission lines. So go read Christina Punzi's 2018 paper. But I didn't have time. I couldn't include everything.
Thank you.
Just by curiosity, in fact, you had that plot, I think it was slide 23 with the different spectral types.
Yeah,
Where does Vega fall in that?
Vega is older and not very dusty. I don't plot things below 10 to the -4. I don't even know why I plot. That's Zeta Lep right there. And Zeta Lep's like pretty dusty, but even that, it's like, no, man, that's probably an asteroid belt. It's okay. Yeah, that's Eta CRV right there. That one's kind of neat. Yeah, no, those ones aren't very dusty. So I think an asteroid belt interpretation for those stars is probably reasonable.
I was going to say all the A-type stars seem to be normal, right? You don't have any A-type stars, very A-type.
Yeah, well, I don't know what's going on there, right? That's a little weird. Where are all the A-type stars? As it turns out, I'm trying to actually look for transits of planets around A-type stars because those also look anomalous and are missing. So I don't know, wait a couple of years, I'll have some transiting planet mass limits or radius limits, I guess, to get out of transit. But yeah, there's something weird here, right? The only A-type star out here is Zeta Lep. They're all clustered over here otherwise. And none of them are huge. Now L star is bigger, but I don't know. Yeah, I mean, when I wrote my paper in 2013 about these two, yeah, I kind of said the same thing. I was like, well, I guess they finish faster. But I think planetary systems around A-type stars are just inherently very different from those around FGK and M's, of course. No M's on there, sorry.
Regarding the disappearing dust or disk,
Mhm.
can you envision a collision between two objects that's violent enough that the dust is ejected at such high velocity that you're just seeing the decay of the black body emission as it gets further and further away from the star?
Well, so I'm glad you asked that. We thought about that. And so,
Yes, we do run over time, so if you need to go, please feel free. But I will say, yeah. Thank you for coming. Yeah.
that's why we took Herschel data. Herschel